Hello, my name is Sifei Luan, and today I'm excited to talk about Exoshuffle, an extensible shuffle architecture. Let's start with the motivation. We're talking about shuffle in the context of distributed data processing. Shuffle happens whenever there's an all-to-all data transfer between all nodes in the cluster. For example, in a MapReduce style system, shuffle happens between the map and the reduce stage, in which every node will send data to every other node. This is a key operation in distributed data processing. In modern data frameworks such as Hadoop, Spark, and Presto, many high-level SQL operators involve shuffle during execution. For example, to select distinct elements, order by, some join methods such as sort merge join, and group by. In each case, the framework developer needs to implement the distributed shuffle operation. So what makes shuffle challenging? Turns out it's difficult to execute shuffle at large scale because shuffle essentially means moving a very large number of very small blocks across all nodes in a cluster. The number of shuffle blocks grows quadratically in the total data size. And when you're processing terabytes of data, this results in more than billions of data blocks, each of only kilobytes in size. This makes the operation difficult to optimize. One, this creates inefficiencies in disk I/O. And two, failures can happen when the system transfers billions of blocks across network, disk, and memory, and the system must be able to transparently handle these failures. Given the importance and the difficulty of shuffle, people have developed many specialized systems for large-scale shuffle. These systems solve the performance and scalability challenges at large scale, but they are costly to develop and to deploy. To understand why, let's first identify the optimizations implemented by these shuffle systems. First, there's a control plane where the system makes decisions about when and where to transfer and to merge blocks. Many research work propose different strategies for merging shuffle blocks. Then there's a data plane, which is a low-level system component that implements efficient data transfer through network and disk. It should also provide fault tolerance. We noticed that in previous systems, the control and the data plane are implemented using low-level frameworks such as RPC, and they are tightly integrated together in the implementation. Therefore, although the primary change is in the control plane, such as changing the timing or the location for merging blocks, because of this tight coupling, these control plane changes require creating a new system, which requires re-implementing a lot of the low-level system components in the data plane. The two problems with existing shuffle systems are that, first, the data and the control and data planes are tightly coupled, making the system hard to develop and to deploy. And two, that they provide limited interoperability with other applications than the synchronous batch processing systems. To solve these challenges, we present Exoshuffle, an extensible shuffle architecture. The key idea here is that we can decouple the control and data planes by implementing shuffle at the application level. We achieve this using the programming abstraction we call distributed futures. This allows us to factor out the common low-level functionalities into the system, which provides an efficient implementation of the data planes. The control plane now offers more flexibility, as the shuffle results can now be passed to downstream applications using the distributed futures, allowing for more fine-grained pipelining. In this preview of the talk, we will show you how the control plane, using the distributed futures abstraction, makes it easy to implement new algorithms and is also flexible enough to interoperate with other applications through fine-grained pipelining. There has been work on distributed data processing implemented on future systems, but their performance has been lacking. We will show that with Exoshuffle, this decoupled architecture can still provide performance and scalability that is competitive to specialized shuffle systems. So now let's talk about system design. We will show you how we can use distributed futures to express shuffle. A distributed future is a reference to an object that can exist anywhere in a cluster and whose value may not yet be computed. You can pass a distributed futures as an argument to remote tasks and immediately get back another distributed future that represents the result of the task. By using distributed futures and remote task invocations in these two lines of code, we can create the shuffle operation in the classic MapReduce paradigm. We use the system Ray. Ray provides the .remote API to turn regular functions into remote tasks. Invoke the remote task, and then we immediately get back the distributed future references, which can be passed to other tasks. For example, in the first line, the map.remote call does two things. It schedules a round-of-the-map task on the workers and also return a distributed future reference that we can use. For each reduced task, we take one input from each map task as an argument and schedule the reduced tasks. This effectively creates the all-to-all communication pattern, or shuffle. For execution, we use the distributed future system Ray. From this simplified version of the shuffle program, we can already see the division of labor between the application program and the system. The application specifies when to start tasks and also the dependencies between tasks. The system, on the other hand, provides a lot of things under the hood. It provides resource allocation, or where to run these tasks. It provides memory management that includes transferring objects between nodes through a network. It includes spilling objects to the disk, and involves garbage collection. Ray also implements pipelined I/O so that the network and disk I/O operations can overlap with task execution in order to maximize parallelism. Finally, Ray provides transparent fault tolerance through lineage reconstruction. Now let's talk about evaluation. The first question we wonder is that, does the Exoshuffle architecture make it easier to implement shuffle optimizations? For this, we look at a few optimized shuffle algorithms implemented in previous systems. In Exoshuffle, in order to implement a new shuffle algorithm, we simply need to change the control plane program, and then it will run on the same unmodified execution system. This makes it drastically easier to implement than to build a full-blown shuffle system from ground up. Therefore, we see more than 10x reduction in lines of code needed to implement each particular shuffle algorithm. Of course, these other systems have more components for productionization, and in Exoshuffle, we just implement the core algorithm. Next, we considered, does Exoshuffle provide the performance and scalability that are competitive with monolithic shuffle systems? For this, we use the CloudSort Benchmark, which focuses on raw shuffle system performance. We run a 1 terabyte sort on a cluster of 10 nodes with attached hard disks. We use Spark as a baseline, and then we can show that we can reach the same ballpark performance as a specialized shuffle system. We can see that the Exoshuffle performance is close to that of Spark, and it outperforms Spark when it implements more optimizations at the control plane level. To test scalability, we scale up the experiment to 100 terabyte of data on 100 nodes. Exoshuffle here exceeds the performance of Spark. Finally, we ran the CloudSort benchmark, which is about what's the cheapest way to sort 100 terabyte of data on the public cloud. We broke this CloudSort record by sorting 100 terabyte using less than $1 per terabyte. This is 37% more cost efficient than the previous world record set by Apache Spark in 2016. Finally, we consider what benefits does Exoshuffle provide to the applications. We show one example here of Exoshuffle improving the end-to-end machine learning performance. Here we integrate Exoshuffle with the PyTorch training framework to train a deep classification model. By using Exoshuffle, we can achieve faster training times through pipeline execution between shuffle and machine learning training, and better convergence rate by being able to randomly shuffle the entire dataset per each training epoch. So this concludes our preview talk. I hope to see you at SIGCOMM' this year.